All right, here we are with types of reactions. So between balancing equations, types of reactions, and then recognizing spectators and precipitates, that's the major focus of this particular chapter when you see it in the homework and on the test. So when you look at types of reactions, look for a pattern. So the pattern that we're going to look for here for combination reactions is look for something like A plus X combining together to make one product AX. So these are typically elements with no charge, not always, but usually. And then these have some kind of positive, negative, crisscrossing kind of action going on. Decomposition reactions are basically the opposite. We take A plus X and reverse it into AX decomposes or breaks apart into A plus X. And sometimes there's other things too. We would call this one a divorce, which is making combination more of a marriage kind of analogy. But this is when you have charges and you give those electrons back to make them back into elements typically. There's other examples as well that are outside of that realm of elements to compounds and vice versa, but that's basically what happens in combination decompositions. You have elements that want to be noble gas-like, and they become noble gas-like. And then with the motivation of some heat, typically, you can take them from their noble gas-like states back to their elemental states. The easiest way to recognize these two, because they're very similar but different, look for one product. Look for one reactant. So notice over here, we have just one product. Over here we have just one reactant. There's nothing else there. And that's the easiest way to recognize those two from all five. As you look at single replacement, imagine that you have an element by itself, A, but then you have this other compound, BX, and then they switch to AX and kick B to the curb. So it's kind of like cheating. A was by itself elementally. B ends up by itself elementally. B was with X because they had charges that crossed, and these had charges that crossed that are probably different and it may need balancing as a result. So when you look at this one, this is called single replacement. It's kind of like cheating or almost like home wrecking in a Hallmark movie. What you notice here is you have one element and one compound, and they switch to a different element and a different compound, or vice versa there. So notice there is no one product, one reactant. It's one of each. A reactant and a product, and a different reactant and a product on the other side. That's a little bit different than double replacement. So in single replacement, notice we only changed one partner. We took A for B and we switched them. X was just along for the ride. We call it a spectator ion. What we notice in this next one is double replacement has two partners. So you have some AZ plus BX, and then you switch both. So now we have AX again, but now instead of kicking B to the curb by itself, it runs off with the other partner Z. So here, different from the other three, we have two compounds making two different compounds. But in all, we have four compounds. Never do we have an element by itself, as is the case for single replacement. Double replacement, we just have ions that are trading places. So we had a plus and a negative here, a plus, a negative in here, and then they switched. No electrons were transferred in that process. So of all the reactions, this one specifically has no electron transfer. All the other ones do. So we'll see combination, decomposition, single replacement, and combustion reactions in the chapter in 2 weeks when we talk about electrochemistry. But double replacement will be a focus for this chapter because it's just trading partners. It's not trading electrons, and that's very different from all these other ones. Combustion reactions probably the easiest just because you're looking for these three pieces. We saw that in a previous video for methane. But here we have some organic, typically carbons and hydrogens. And again, they can be lots of different things. They can even be alcohols or ether-based. But what doesn't change is specifically you have O2 to burn it, and then you end up with CO2 and water. So different from all the other ones, these three pieces have to be in place in order to be combustion for our textbook. So if you don't see O2 as a reactant and you don't see CO2 and water as products, it can't be combustion reactions at all. It has to be one of the other four types. So again, look for take-home messages. Do you have one product? If so, combinations like getting married. Do you have one reactant? If so, it's more like a divorce. It's more like a decomposition. Do you have somebody by itself as a single, and you end up with somebody by itself as a single? Or is it double replacement because you have a married couple and another married couple, and they either swing or trade partners like the TV show Wife Swap, and they become new partners temporarily? And then lastly, specifically, do you have O2, CO2, and water? If not, if this isn't there, then it's not combustion whatsoever. So those are the clues to recognize reactions in our course. So let's look at combination briefly. Combination is like marriage. It's like the H2 plus I2 gives you HI. So notice what happened here is we had elements that have no charge, but they end up with something that is like charge, having this kind of +1, -1 interaction that we would have saw in week 1. But more importantly, this was more Lewis dot structure related because of the 1-valence and 7-valence electron ideas. They're also called synthesis reactions because you're making something. Here you're making HI, which is hydrogen iodide or hydroiodic acid if it were dissolved into water. Typically this can happen if you react metals with oxygen, non-metals with oxygen, or any metal with any non-metal. So you're basically looking at the periodic table and you're saying, take somebody from over here and take somebody from up there and then allow them to trade electrons. Just remember that these guys here are the losers. They're going to lose electrons. These guys over here are going to gain electrons. And then that electron transfer process is why combination reactions are irreversible. You're going to have to really motivate them to divorce them back from their noble gas kind of configurations. So here's a couple examples. We have magnesium and oxygen making magnesium oxide. We actually did this in one of our first experiments. We just didn't know what it meant at the time. We were just observing its chemical change. What's important for us to realize here is this is just A plus X gives us AX, just like we'd expect it to be for combination. Produces a lot of heat, so definitely a chemical change. And this is a reaction with metals and oxygen gas. If we look at nonmetals and oxygen gas, notice we have that weird S8 for sulfur. That's that octameric sulfur we said to watch out for. But generically speaking, this is just A plus X, and it gives us this AX compound. So it's marrying together sulfur and oxygens. Obviously, because of this 8 and because of this 2, you're going to have to balance that equation as they've done already for us. But here we're just looking for that pattern. And it has elements becoming a single product. And that's what we're after. Here we can just about take any metal with any nonmetal and still have it work. So again, it fits that formula of A plus X gives us AX. We have that singular product, although we have to balance it in this equation because of the diatomic chlorine. Gets a little bit trickier with transition metals because they have multiple charges, so we tend to avoid those in introchem specifically, because you can have 3s and 2s for irons or 1s and 2s for coppers and so forth, all that Econo stuff that you probably wish you could forget forever. That kind of stuff is hiding behind the scenes here, but we tend to stay away from it and look at these more generic examples using main group metals and, in this case, halogens. The flip side of a coin is decomposition. Decomposition is kind of like divorce, opposite of combination. So decomposition is when we have one product, but then we break it into multiple pieces. So it's like taking this married couple AX, and then we force it apart into A plus X. A lot of divorces are a little bit different because sometimes they have other, kids and other, houses or cars or whatever that have to be separated. So not all decompositions are perfectly, split into half like this one looks like it did. But what's most important is it had that single reactant. And if you have that single reactant, you can break it up into many pieces, and that's decomposition. So let's look at a couple examples. Here we have mercuric oxide, which is that kind of red dust you see in the test tube in this picture. What's most important, though, is you realize this is just married AX getting divorced back into A plus X. X happens to be a diatomic gas, so that subscript happens to be there. But again, most importantly, it has one reactant, and that's what makes it a decomposition, a divorce. So mercury oxide here, so this is mercury 2 oxide, this is mercuric oxide. This is a +2 and a -2. And only with the Bunsen burner heat is this possible. So these are already noble gas-like, they're already perfectly happy. But if you heat them up to, 1,1500 degrees in a Bunsen burner flame, you can motivate them to give those electrons back and make them elements again. So that when you tip this tube over, little mercury, liquid balls run out the test tube, and there's ways to test for oxygen gas that we'll see in lab coming up as well. But again, big picture idea, one reactant. That's different than what we saw a moment ago with one product for combination. A common decomposition is carbonates. So you can take carbonates or hydrogen carbonates and get them to break apart. So notice we do see kind of a hybrid here of an AX, and then we get an X, and then something else. So that is possible. But again, we only have one reactant. Down here it's a little bit nicer. We have AX and we get A plus X. So even though they're not elements, notice there's still one reactant and then multiple products. This is a fun way to realize that if you want carbon dioxide, all you need is carbonates. Calcium carbonate is a majority of limestone. So if you have volcanic activity underneath calcium carbonate or limestone, it can actually heat it up and decompose it so that carbon dioxide bubbles can bubble to the surface. If you bottle that up, you can have natural carbonated water. So, club soda, so to speak, sparkling water. And then we get to single and double replacements. Single and double replacements are a little bit different, so we're going to cover those in a separate video.